Okay, good afternoon everybody. My name is Rebecca Boston. I'm acutely aware that I'm the only thing that stands between you and lunch, so hopefully this will be on point. So I started a research fellowship last December, co-sponsored by the Lloyd's Register Foundation and through the Royal Academy of Engineering. I'm based at the University of Sheffield and I'm in the Materials Science and Engineering department. So today, what I'm going to give you is a little bit of an overview of where my career has been so far, and one of the research highlights from that, and where I'm going next. And hopefully there will be, for the PhD students here, there will be some useful nuggets of information that I've picked up along the way so far. Hopefully they'll be useful for you. So, I work in nanoscience, so we start small. I started off as a physicist, doing a master's at the University of Bristol, and like all good physicists, I wanted to be an astronomer. So, started off down that path and then realised within about a year that most of astronomy is maths, and so decided that that perhaps wasn't quite as exciting as looking down telescopes as I thought it might be. And so instead, in my third year, I started looking at microscopes. So I've gone from the very, very large universe to the very, very small universe. And I had the opportunity to use a TEM, do some AFM, and this led on to a real fascination with nanoscience and things that are very small. So in my final year, I focused on the nanomechanical properties of pollen, and that led quite nicely onto a PhD at Bristol with the Bristol Centre for Functional Nanomaterials, which is one of the CDTs that they run there. And I had a whole range of projects in my first year. I was looking at microfluidics, a bit more AFM, a bit of clean room fabrication, which I think some of you were doing yesterday, and some point-of-care diagnostics. And it was this point-of-care diagnostics that I really thought was going to be where I was going to go. I was going to stay in the sort of biophysics area. Unfortunately, that project, or fortunately in my case, that project didn't fly. And I kind of jumped in with both feet to a project that I knew very little about. And I've actually ended up working in oxide superconductors and the bio-inspired synthesis of them. And that actually went pretty well. And so what I've then done is gone on to a postdoctoral research position at the University of Sheffield. And in particular, I was taking the ideas that I'd learnt during my PhD and applying them to a new material, a new set of materials, which are capacitors. So I'm going to talk a little bit about the techniques that I use, so a bit of science, and then we'll go back to a bit more of an overview. So, in terms of keeping things nano, biotemplating has emerged as a really flexible and exciting new technique for making oxide materials. So let's say if you wanted to make barium titanate used in capacitors, you've probably got 100 or so sitting in your mobile phone right now. Normally to do that you would take some barium carbonate and some titanium dioxide, mix them together, make them quite small, although for nanoscientists quite big, 10 microns, 1 micron, huge for what a lot of us are working on. And then we'd heat them up, and heat them up for potentially a really long time, anything from about 24 hours to maybe a couple of weeks, and wait for those materials to react really slowly. And that's fine, it works really well. There's billion-dollar industries based on these technologies, but it's incredibly energy intensive. It costs a lot of energy, it costs a lot of money to do. And so what I'm interested in is finding new ways we can control the growth of crystals in these oxide materials, but that take less energy and take less time. And hopefully by controlling their structure, we end up with a better product at the end. And that's where biotemplating comes in. So biotemplating uses biopolymers. These are materials that we find in nature. It might be a simple sugar, something more complex like sodium alginate that we would find in seaweed, through proteins right up to macroscopic structures such as pollen or cuttlebone. And what we do is we take the properties of these materials and use them to direct the structure of oxide materials as they grow. So you can see, hopefully it's not too small, on some of the biopolymers we have functional groups, something like a hydroxyl carboxylate group, which when in water dissociate or deprotonate, forming negatively charged regions. Now if we introduce a positively charged metal cation at this point, you get some interaction and we can form a composite material, as we can see here. This is an idealized structure, obviously it's not quite as beautiful as this. We then heat these materials up, and as the organic component burns, leaves up the chimney, we're left with an oxide, hopefully of the material that we want, but we can also start to introduce some structure. So if we start with some dextran in a spherical shape, we end up with an oxide in a spherical shape. We can grow nanowires, we can grow foams. So it's a really interesting technique. So here are some of the examples of things that we can make. We've got some nanoscale foams on the side. We've got some spherical nanoparticles. They're not nano themselves, but they're made up of nanocrystals and they're hollow, so we can start to backfill with other materials. We have hierarchical layered structures, which are really nice, using graphene oxide. And most interestingly, we can use sodium alginate, which is our seaweed derivative, to grow nanowires in oxide materials that we really shouldn't be able to grow nanowires in. And this is probably worth a little bit more exploration. So one of the most important things for science, as far as I'm concerned, is to be able to stand and watch something, see it with your own eyes. Now, nanoscience makes that inherently really difficult because everything is so small. But what we wanted to do with these nanowires was take the samples, heat them up, and watch them grow on the nanoscale. And that's exactly what I did. So I went over to the National Institute of Materials Science in Japan, where they have an in situ heating stage for their transmission electron microscope, their TEM, put my samples inside and watched the nanowires grow. So hopefully this will work. I have a video of one of the nanowires growing. So you can see that we are well and truly on the nanoscale here. This is an 8-minute video. I've sped it up because otherwise we will be here all day. But you can see that the nanowire starts to emerge as we raise the temperature. So it really gets going in a minute. So there we go. So this is a superconductor nanowire, although obviously not superconducting at the moment because it's very hot rather than very cold. And what this led to was the discovery of a completely new nanowire growth mechanism. So vapor liquid solid growth, where the droplet of liquid is on the free end of the nanowire, is well known. But what we have here is the microcrucible mechanism, where the droplet is on the base of the material and the nanowire grows outwards from the surface. And this is incredibly exciting. We get nanowires of uniform cross-section, really useful for applications. And it turns out we can do that in a huge number of different materials, and as has been seen previously in the literature. So we've got some PZT here, we've got a few superconductors and a dielectric material as well. So that's been a real highlight of my work so far. And it's really helped me to choose the direction that I've been going in since my PhD. So in order to grow my research, I started small, as a good nanoscientist would, just with one technique, biotemplating, and one set of materials, oxide superconductors. But I quite quickly realized that academically interesting though superconductors are, the real world is not necessarily just about academic interest. We need something that we can use. So for my postdoc, I decided to take the ideas of biotemplating and find a position where I could apply them to something more useful, in this case, dielectrics. I then included a few other new techniques, so solid state, solvent templating, a few new things that I can use to improve my research. And then realizing that, of course, dielectrics worked really well. For my fellowship, I then had a look at what else could this technology be applied to, and that's really what I'm working on at the moment. So I've taken the idea of biotemplating right from my PhD, right through to my fellowship. I've hung on to the dielectrics, and I've introduced a range of other materials as well, where this technique could be really useful because we're working on the nanoscale. So that includes things like lithium-ion batteries. We've got some thermoelectric materials in there, some really exciting things going on with that. And then I started talking to my colleagues as well, and they all thought it was quite an interesting technique. So now I have a huge number of collaborators as well, and that's expanded my range of materials even further. So now into lithium-ion batteries. I've got some really exciting things with fusion materials, and some slightly left-of-centre life cycle analysis, which is really important if we want to say that our materials are sustainable. We need some numbers to prove that. And of course, I can't do that on my own. So I now have a group of students. I'm just about to gain a couple of PhDs, which is really exciting, and some fantastic masters and undergrad students as well. So really the key message that I found so far in my career is that you've got to find an application. Find something that you're interested in, find something that you love, but find an application for it. There's no need to just do something for academic interest. That's great, but funding requires application. And to do that, you're probably going to need some friends. So application and collaboration is absolutely key to your future careers. And I've got one final piece of advice for the PhD students. Do other things as well. The science is fantastic. It's brilliant, it's great fun, you love it, that's why you do it. But there will be times that you need to get out and do something else. And so these are some of the things that I do. I'm a fell runner, so I'm out on the Peak District fells running every week. I sing in a choir. I love walking. This is me on New Year's Day on top of a mountain in the Lake District. Freezing cold, so cold, cannot tell you how cold it was. And I also drive a racing car through the summer, so it's just a few things that keep me going when the science gets tough. So thank you very much to all of my students. This is an ever-growing list now, which is incredibly exciting. And to my collaborators, the top 4 at the University of Sheffield, we've got collaborators at NIMS in Japan, University of Birmingham and Penn State University. And thank you to my funders, of course, the Lloyd's Register Foundation, without whom I would not be here, and the Royal Academy of Engineering. And thank you very much for listening.